In this series of videos, I'll try to discuss the problems on control system. I'll show you how easily we can tackle the problems on control system. There are several important topics in this control system: transient response of the systems, condition for stability of the systems, Routh-Harwich criteria, root-Lucas technique, Forer plots, Nyquist plots, Bode plots, and state space analysis. Okay, we'll discuss all the topics one by one. In this video, we'll focus on Bode plots. I'll show you how to handle the problems from Bode plots. The first problem we'll consider this one. So this problem is from GATE 2019 Electrical Engineering. One asymptotic Bode plot for magnitude response is given. G of g omega, its magnitude. This is the figure. X-axis is your W, the frequency in log scale, and y-axis in dB. Now for this figure, the question is that here it is said, consider the following two statements. First statement is transfer function g of s has 3 poles and 1 0. And second statement is at very high frequency, that is omega tends to 0, the phase angle g of g omega is equals to minus 3 pi by 2. Now we need to find out whether these statements are correct or false. Okay, accordingly these choices are given. So first choice is statement 1 is true, second one is false, this one is statement 1 is false and statement 2 is true, and C option, both statements are true, and last one is both statements are false. So how to identify these two statements? So it's not a difficult problem. You follow my approach. I'll consider this figure. We'll try to find out g of s. From this figure, this is a magnitude plot for g of g omega is provided. From that, we'll try to identify the transfer function. And if I know the transfer function, we can find out poles and zeros, right? Now, let's look at this figure. This figure is having one initial slope. Whenever you will get one initial slope from very small frequency to right side, okay, whether it's decreasing or increasing, some slope is given, then obviously there is one poles or zero. Okay, so if you find one downward slope, and that is minus 20 dB per decade, this negative sign indicates that it is decreasing. Okay, so if you find one negative slope like this, minus 20 dB per decade, then it is due to one pole at origin. That means g of s is having 1 upon s. This one. Because of this gain is falling by 20 dB per decade. Similarly, if you have positive 20 dB per decade, some increment like this, then obviously that is for 1 0 at origin. Okay, so if you have positive slope 20 dB per decade initially, then we have 1 0 at origin. If I have negative slope minus 20 dB per decade, we have one pole at origin, right? So as it is given here, minus 20 dB per decade, it is one pole. And if it is minus 40 dB per decade, 2 times of that, then I should have 2 poles at origin. Similarly, if I have minus 60 dB per decade initial slope, I'll have 3 poles at the origin, means 1 upon s cube. Okay, in that way. So for this problem, this initial slope, it is 1 upon s. Okay, I think it is clear. Next, I'll consider next slope. Now here I'll see the changes. So from minus 20 of decade, now at this point when omega equal to 1, from that onward the slope is changing from minus 20 dB to minus 40 dB. So another minus 20 dB is added. This additional minus 20 dB per decade gain, it is due to one pole. So you understand that pole will decrease the gain and 0 will increase the gain. Okay, if you find negative additional negative slope, then it is due to the pole, and if you find positive additional slope, then it is due to the zeros. So here there is minus 20 dB additional slope, thus we have one pole at this point is equals to minus 1. We write in this form 1 upon 1 plus s by 1. So if it is a, then I write 1 upon 1 plus s by a. Right? So this slope will is continuous till this point, this omega equal to 20. Okay, so this part is due to this pole. Right? Next, here again we will have one change. So earlier it was minus 40 dB per decade, and from here onward we are getting minus 60 dB per decade. So again another 20 dB decrement, means minus 20 dB per decade change is there. Thus we have another pole located at s equals to minus 20. Okay, so we write 1 upon 1 plus s by 20. So these points are called corner frequency. This 21, these two are corner frequency. So here we are getting at this point, at this junction, we are getting the changes. Right? So these are the three poles in the system we should have. Thus, we can write G of S can have in this form. So it can have one DC gain K. Okay. And because of this say one pole at origin and one pole here at minus 1, 1 plus s, and another one is one pole at s equals to minus 20, means this term 1 plus s by 20. Okay, so you multiply all those poles. Okay, and if you have some zeros, you will multiply those zeros here in numerator, and you will put one constant k, and from the figure we can find out the k value. So here at omega equal to 1, its value is provided plus 40 dB. So from this information we can find out the value of k, but for this problem it is not required. So now consider the statements. The first statement, transfer function g of s has 3 poles and 1 0. Is it true? It's not true, because this system is having 3 poles but no zeros. I don't have any zero, because function is not increasing, function is always decreasing, starting from initially minus 20 dB slope, then minus 40 dB per decade, then minus 60 dB per decade. Always it is decreasing, means it is having only the poles. There is no zeros. So first statement is wrong. Okay. Now second statement, the statement 2, at very high frequency, means at omega tends to infinity, the phase angle g of j omega is minus 3 pi by 2. So we need to find out the phase angle. Okay. And g of j omega, from g of s, if I replace s by j omega, I'll get g of j omega. So everywhere I replace s by j omega. So it is k, this is j omega, 1 plus j omega, this is 1 plus j omega by 20. So this is one complex function. Easily we can find out the magnitude and phase. So what is the phase? This angle of g of j omega. So this DC, this constant will not provide any phase. This J means 90 degree. Simple J means 90 degree. As it is pole denominator, that it is minus 90 degree. So pole will provide negative phase and 0 will provide positive phase. Okay. So this pole is providing minus 90 degree. The pole at origin. Second, this phase is tan inverse omega upon 1. So the minus sign, because of this pole, minus tan inverse omega upon 1. And for this one, it is minus tan inverse omega upon 20. That's all. Okay. So this value and this value. So this is your total phase. And if there is any 0, then I will have some positive phase. But in this case, there is no 0. So thus all the phase are negative. Now we'll consider omega tends to infinity. At omega is approaching to infinity, tan inverse omega, it means tan inverse infinity, is nothing but pi by 2. Again, this one, tan inverse infinity by 20 is again infinity. Tan inverse infinity is again pi by 2. So this is pi by 2, this is pi by 2, this is again pi by 2, means minus 3 pi by 2. So second statement, this total angle is minus 3 pi by 2 at omega tends to infinity is correct. Thus, the first statement is false and second statement is true, means choice B is correct. Okay, I hope this is clear, right? So you can note here. So if you find, again I repeat this thing, that there is an initial slope. Okay, so this slope minus 20 per decade, it is continuous on both sides. This is the exact plot. So this Bode plot is actually asymptotic plot, some approximate plot. But if we have a pole at origin or 0 at origin, that plot is exact plot. Okay, so here it is an exact plot. It is continuous in both sides. It is decreasing, starting from very low frequency to very high frequency. The gain is falling, and rate is minus 20 dB per decade. This is for one pole at origin. If I have two poles at origin, the slope will become minus 40 per decade, again continuous, steep one. Then if minus 60 dB, then 1 upon SQ, 3 poles at origin, like that. On the other side, if I have a 0 at the origin, I'll have positive slope plus 20 dB per decade. Right? Similarly, if I have plus 40 dB per decade, I'll have two zeros, means a squared term. Similarly, for plus 60 dB, SQ terms, like that. Now compare this one. If I have a gain function g of s equals to 1 upon 1 plus s upon a, means one pole at s equals to minus a. That time, the corner frequency is omega equal to a, and when omega is very less than a, then the approximate gain is 0 dB. It is not providing any gain. Means if omega is very less compared to this one is I can ignore. And dB scale 20 log of that gain, means log of 1 is 0. Okay, and this side it is having a negative slope, minus 20 dB per decade. So just look at this one. If I have a pole at s equal to minus a, the corner frequency is omega equal to a, and when omega is less than a, it is 0. Omega more than a, one slope minus 20 dB per decade. Okay. Similarly, for zeros, 1 plus s by a. Omega less than a, it is 0 again. But for omega more than a, there is a positive slope plus 20 dB per decade. Okay. Similarly, if I have a plus 40 dB per decade, I'll have two zeros at the same point s equal to minus a. Means function will be 1 plus as upon a, that square. Okay, like that. Okay, now if figure is given, how to get the inverse thing, means transfer function. So you need to find out the change in slope. If there is a change of minus 20 dB per decade in slope, then obviously it is due to one pole, right? And if you find a change of minus 40 dB per decade in slope in some places, obviously it is due to the two poles at the same place. Okay. Similarly, if I have a positive change plus 20 per decade in slope, then obviously it is for 1 0. And if I have plus 40 per decade in slope, 2 zeros. Similarly, for 60 per decade, 3 zeros, like that. Okay, this is the basic information we'll be using. Okay, we'll move to the next problem. And before that, is the video useful to you? And if you think it is useful, then may I ask you to press the like button? Okay, so you decide, and if it is useful to you, please press the like button. Now we'll continue. We'll go to the next problem. The next problem is this one. It is from GATE 2010 from ECE Electronics. Now again, one figure is given. The asymptotic Bode plot is mentioned, and we need to find out the system transfer function. That is a simple problem again. Okay, you can now solve it. You can pause here, you can solve it. Okay, now I'll solve for this one. Now look at this one. There is no initial slope. Okay, so this is 0 means there is no initial slope. Initially means there is no 0 or pole at origin. That is confirmed. Okay, and from here there is one slope, right? And from here there is another change. This slope we need to understand first. So what is the rate of the slope? What is the rate? Okay, the magnitude of the slope. So this slope we can find out. So you see this value is omega equals to 0.1 and that is equals to 10. So this increment is 100 times. So 0.1 to 10, 10 by 0.1 means 100 times increment. And that time the magnitude change is 0 to 40 dB change. Okay, and so if I consider one point in middle, so obviously it will be 1. So it is 10 times, then another 10 times, total 100 times, because it is in log scale. So this is 0.1 to 1, it is 10 times, and it is middle, and its value will be plus 20 dB. Okay, so this change is, this gap is 20 dB. So this gap is 20 dB for one gain, 10 times gain, and 10 times gain is called 1 decade. Okay, for 1 decade there is a change in magnitude plus 20, thus slope is plus 20 dB per decade. Okay, so here also we can consider, so here's 2 decades, because this is 1 decade, 10 times, another 10 times, so 2 decade. In 2 decade there is a magnitude change of 40 dB, so rate is 40 by 2 means 20 dB per decade, right? I hope it is clear. So this slope is 20 dB per decade, not 40 dB per decade. Be careful, because this is 0.1, this is 10, this is 100 times, means 2 decade. That's how it is 40 dB change. So slope is 40 by 2, that is 20 dB per decade. Okay, so as it is having plus 20 dB per decade, obviously it is due to 1 0. Okay, so I write g of s equals to some constant k times 1 plus s upon a. This a is here 0.1. Okay, this is the corner frequency, so s by that corner frequency 0.1. So this is for, so this slope is for this 0. Okay, next one is this one. Okay, so you see this slope is 0. So what is the change? So plus 20, now it is becoming 0 dB. So change is 0 minus 20, means minus 20 dB. So now someone should provide minus 20 dB. Then from plus 20, now it will become 0 dB, right? So here this change is obviously due to this slope minus 20 dB per decade, right? So now you can easily understand that as change in slope is negative and it is minus 20 dB per decade, so obviously it is due to one pole, and pole position should be at this point, means s equals to minus 10. Thus I should have one pole here, and that would be 1 upon 1 plus s upon 10. So this is the transfer function, and now the k is not mentioned till now, right? Now we need to find out this k value, right? Now here easily you can understand from the choice, so no need to provide or find out the k value, because in numerator it is 10s plus 1 or 100s plus 1 or 100s, 0.1s plus 1. So all are different. So in numerator you can see it is 1 plus s by 0.1 means 10s. 10s plus 1. So 10s plus 1 is only one choice A. So we can skip this part. No need to find out the k, and k will be 1. Why? Because the initial gain is provided 0 dB. Means there is no level shift. Thus k equal to 1. So if initial gain is 0 dB and there is no slope, then obviously k equal to 1. And if it is other than 0 dB initial value, then it is due to some constant k. Okay, we need to find out that value, right? So this is important thing. 0 dB initial gain with 0 dB for decade slope. There is no slope is given. Then obviously k equal to 1. So we can put k equal to 1. And so its value is 10s plus 1 upon, and this is your s upon 10 means 0.1 s plus 1. So option A is correct. So it's now very easy to solve. Now we'll move to the next problem. So third problem, again one figure is given. It is from GATE 2007. So you see every time one function is provided and this plot is given, asymptotic plot, from that we need to find out the transfer function. So that type of problem is coming regularly. And from the plot we can find extra things like gain margin, phase margin, but those things are coming rarely. Okay, we'll discuss later. Now how to find out the gain function for this one? So already we have discussed this figure probably. Okay, quickly we'll do that one and we'll find out the exact transfer function. Okay, now you see there is one initial gain, so the rate, that rate is minus 20 dB per decade initial slope. So obviously it is for one pole at origin, 1 upon s. There is a change from minus 20 to minus 40. So additional minus 20 dB, one pole, and pole at this point. So 1 upon s by 1 means 1 upon 1 plus s. And this is another 20 dB addition. So another pole, 1 upon 1 plus s by 20. Very simple. So GS will be of this form. K upon s into 1 plus s times 1 plus s upon 20. Now what is the value of K? That is the important. Okay. So in this problem it is required to find out the K value. And here you see this one. This one value is provided here and one more value is provided here. You can use any of this one or this one. Okay. Anywhere from all the points we can find out the k value. Okay, I'll show you how to find out the k value easily, right? Now before that, try to understand these things. So already I've discussed that if there is a pole, then will get one slope minus 20 per decade continuous. It's the actual plot, no asymptotic thing. It is continuous both sides, and it will pass through omega equals to 1 at 0 dB. So this is 0 dB line, and omega equal to 1, it will pass through, because at omega equal to 1, its gain will become 1. 1 means 0 dB. Okay, and if I consider this function gs equals to 1 upon 1 plus s, then its corner frequency is omega equal to 1. So when omega is less than 1, it is 0 dB. More than 1, it is minus 20 per decade. And for this fall, the corner frequency is 20. So the left side is 0 dB, and right side there is a slope minus 20 dB per decade. Now try to understand. If I consider that, suppose point 1, at point 1, who will contribute? At 0.1, omega to 0.1, this function will contribute, because it is having some non-zero values. At point 1, probably here some values will be there. So it will be 20 dB, obviously, because the gain will be, this side is plus 20, 1 decade. 0.1 to 1 is 1 decade. So this change should be 20 dB. Okay, that is one thing. But it will not provide any gain, because at point 1, its approximate value is 0. At point 1, its approximate value is 0. Okay, so at point 1, S will contribute, this will not contribute, this pole will not contribute, but K is always contribute, because will contribute if it is other than 1, right? So at point 1, resulting magnitude is due to this K and the pole at origin. That's all. Similarly, at 1 also, at 1, this pole will contribute at origin, but this will not contribute, because it is approximately 0. This is also 0, perfectly 0. So at omega to 1 as well, only this pole at origin will contribute. This pole at s equal to minus 1 will not contribute, and pole at s equal to minus 20 will not also contribute. So I can ignore their contribution. I can imagine that the gain function g of s is simply k upon s. If I want to find out the approximate magnitude at omega equal to 1, okay, at omega to 1, its magnitude is given plus 40 dB. That information I can use it. Okay. So what is the magnitude? G of j omega at omega to 1, and that is provided. At omega to 1, its value is plus 40 dB. So here I replace s by j omega, and I'll consider that only k and s, they will contribute. I'll ignore these two. Okay. So here s is replaced by j omega, and its magnitude when k equal to 1. So its magnitude is k upon omega, and omega equal to 1, thus it is k upon 1 is k, right? So this magnitude is given in dB scale, means 20 log of that gain. That is in dB scale, 20 log base 10. Okay. Thus 20 log base 10 of k is given 40 dB. Now we need to solve these things and to find out k. So this 20 and 40 to cancel is by 2. Okay, so log k base 10 is equal to, so k equals to this 10 and square means 100. So k equal to 100. So I can replace k equal to 100. So you can see that we can find k equal to 100 from this point. Similarly, we can find the k value from this point as well. It is given 60 dB at 0.1. You can see this one. K by 0.1 equals to means 10k. So 20 log of 10k will be 60 dB. If we solve, then what will happen? log 10k upon 10 will be 3, means 10k will be equals to 1000, so k will be again 100. Okay, so from any point we can understand these things. Okay, so this k value I can replace this one 100. So if you simplify it, this is 100, it is s, 1 plus s, this is 1 plus s by 20 means 0.05 s. Thus the answer D is correct. It's simple. Okay, it's very easy to find the k value. Now we'll go to the next problem. This problem is taken from GATE 2019 ECE paper. Now for an LTI system, this Bode plot is provided. Okay, now from this figure we need to understand the number of system poles NP, number of system zeros NZ in the frequency range 1 Hz to 10 to the power 7 Hz. Okay, so 1 Hz means from here to 10 to the power 7 Hz here. This is 10 to the 7 Hz. So in this range, how many poles and zeros are there? Those we need to find out. Just only numbers. So this problem is very easy. Just you need to understand the change in slopes. So already I've said that if there is a change in slope, in negative change in slope, it is due to the pole. If there is a positive change in slope, then obviously it is due to 0. And if it is negative minus 20 per decade, it is 1 pole, and minus 40 per decade, 2 poles. Similarly, plus 20 per decade, 1 0, plus 40 per decade, 2 zeros. Similarly, plus 60 per decade, 3 zeros. In that way. Okay. Now we'll start. Okay. Now in this figure, you see this first one, initially it is given 0, it is fine. And from that, this is the corner frequency. At this corner frequency, there is one change in slope. Okay, so as there is no DC gain, sorry, no initial slope, so there is no pole at origin or no zero at origin. Okay, and this shift is due to DC gain K. So this change minus 20 decade, obviously it is due to one pole, and pole will be at S equals to minus 10. So it is GS equals to 1 upon 1 plus S upon 10. Okay. Now again, from this minus 20 per decade, now this slope is given minus 60 dB per decade. So what is the change? So additional minus 40 dB added. So with minus 20, minus 40 is added, then we will get minus 60 dB per decade, right? So this change minus 40 dB per decade, thus we should have two poles, right? So this is the two poles, and then what will happen? From here again, you see minus 60 dB to minus 40. So with minus 60 plus 20 is added, thus we are getting minus 40. So change is plus 20. So plus 20 is added, thus there should be 1 0 at this point. Okay, at 0 at S equals to minus 20 per 3. Then this one, this is your minus 40. Again there is a change from minus 40 to 0 dB per decade. So this change is plus 40 dB per decade. Okay, so plus 40 dB per decade change is there. That is due to obviously zeros, but two zeros. One zero will provide plus 20 dB per decade. So as the rate changes plus 40 dB per decade, thus there should be two zeros here at the location 10 to the power 4. S equals to minus 10 to the power 4. Now it is 0 dB decade. Then again here. So this is again minus 40 dB. With from 0 it is becoming minus 40. So it is minus 40 dB per decade change. So it is due to 2 poles. Okay. Then another change here at 10 to the power 5, 6. Okay. So another 20 minus 20 dB per decade added. So obviously it is due to another pole, and pole it at 10 to the power 6 means GS is 1 upon 1 plus S upon 10 to the power 6. But this is not required. We need to find out number of zeros and poles. So already we have got it. Okay, can you see? So this is 1 0 here because of this one pole here. Okay, one decrement. Another decrement here, 2 more poles. Okay, and here there is one decrement, 2 poles, 40 dB per decade. Here there is one more pole. So 1 plus 2 plus 2 plus 1. Total is 6. So there are 6 poles, NP equal to 6 poles. Okay. Similarly, the zeros. We have got here 1 0, and here because of this change we have got 2 zeros. So 1 plus 2 is total 3 zeros. So we have 3 zeros and Z equal to 3 and NP equal to 6. Thus answer B is correct. Okay. Now we are moving to the last problem. This one. This is taken from GATE 2013 ECE paper. Now this figure is again one Bode plot is provided, and from that we need to find out transfer function g of s. Okay. Now look at this figure. Only the straight line like that, continuous straight line. Already I have mentioned, if system is having a continuous straight line, it is not approximate plot, it is the exact plot, and it is due to zeros or poles at origin. As it is a decreasing slope, negative slope, so obviously it is due to pole. Now we need to find out the slope, exact slope. Then only will be able to decide whether there is one pole or 2 poles at the origin or 3 poles. Okay. Now what is slope? Now this point is given 1, this value is given 10. So 1 to 10, 10 times means 1 decade. So omega is changing from 1 to 10 means 1 decade change. And by the time, what is the phase magnitude change? So magnitude is falling from plus 32 to minus 8. So total gap is 40. So minus 8 minus 32 is minus 40 dB per decade. Because one decade there is a fall of 40 dB. So it is minus 40 dB per decade in one decade. So slope is minus 40 dB per decade. So you know that if it is minus 20 per decade, then there is one pole. If it is minus 40 per decade, 2 poles. And obviously it is at origin because it is continuous. It is not asymptotic. Okay. Thus it is 1 upon a square form will be there. So 2 poles at origin, g of s will be of this form, k upon s square. Now we need to find out this constant k again. Okay. So how to find the k? So you can take any value. So at omega equal to 1, its value is provided 32. That we can use it. Okay. So here at omega equal to 1, g of j omega, its magnitude is given 32 dB. That information we can use it. So g of j omega, here I can replace s by j omega. I'll get k upon j omega, that square, its magnitude I want. So it is j square equal to minus 1. So k upon minus omega square, but its absolute value will be simply k upon omega square. and at omega equal to 1, its value is k upon 1 square, but this scale 20 log of that magnitude, 20 log of k upon 1 square, it is given 32. So I need to solve this thing to find k. So 20 log of k will be 32 upon 20 means 1.6. So k equals to 10 to the power 1.6 and value is 39.8. Thus k is 39.8 and it is having two poles at origin. Thus g of s is 39.8 upon a square. So answer B is correct. Okay. So we'll continue this one. We'll discuss more problems. We'll discuss different topics. We can consider Nyquist plot, polar plots, all those things one by one. And if you enjoyed this video and if you have not subscribed yet, you may subscribe this channel. We'll be discussing more problems. Okay. And if you have enjoyed this video again, you may share this one to your friends and you may press one like button. Okay. Thanks for watching. We'll continue.